answers. And then if anyone had homework questions, remember your Delta Math is due tomorrow. I did go ahead and push out the Khan Academies that are due on Thursday. So if you've not signed up, you've not seen that, make sure you sign up. And when you sign up, because I pushed those out, I'll need to add you to the assignment, so it'll take a second. For number 1, 4x minus. What did we get for that one? I heard 11 and I saw 1. I did see both of those as I walked around. So let's actually solve this. Walk me through how you solve this.
Take away 4x from both sides.
Okay.
Get negative 10 equals 2x.
Okay. So I believe if you did something instead of maybe you started with 6x or 4, it doesn't matter, and you didn't subtract, maybe you added, or when you added or subtracted one of the constants somewhere in there, you got 11. So just double check that math. 1 is the answer you should have gotten for that one. Anyone need me to check theirs to see where they're wrong? Okay. Number 3, you didn't really need to solve, and we haven't actually talked about this yet. So when I look at this, I'm not going to rewrite all of it. I'm just going to rewrite this last line. And it asks, what does Andre's work show us about the type of solution to this equation? Well, 1, can this be a solution?
No.
No, because this is not a true statement. And as we'll see today, as we go through some examples, you'll see that this is a type of solution. But yes, that reason is because it's not a true statement. They don't equal one another. Hold on to this because we'll do the other 2 tomorrow. You could have already did that, and that's fine. We are going to finish the notes we started on Friday, so go ahead and take a second to take those out. Yeah, you need one. I don't remember if I asked if you wanted to see 1 or 2. If you said no, or if I asked. I'll ask again. Do we want to see number 1 or number 2 worked out? If not, we can move down. We're going to do number 5 for sure. And then of the ones left, we can do 1 more, we can do a couple more. It's really up to you guys. Number 6, 7, 8, and 9. Are there any of those that you would like to see worked out? Number 7. Any others? So we'll do 5, we'll do 7. And then I'll give you some time to work through those, and then we'll go on to our last last set of notes for this. So for number 5, there are two ways to go about it. I'm not going to do both, but if you need it, or if you want to see that second way, we can definitely do that. One way would be just to distribute how it is. A lot of the time, I won't say like most or always, when you have a whole number in a fraction, most of the time or some of the time, this fraction will just simplify with the numbers you have. Sometimes that is not the case though, and you end up with just more fractions. If you wanted to get rid of the fraction, you could also multiply by something to get rid of that as well. When we multiply this 1/3, everything here, instead of thinking about it as 1/3 times 24m and 1/3 times 12, think about it as 24 divided by 3 and 12 divided by 3. That way, in my mind, it's easier that way. Multiply 6 to everything here. We get 30m minus 18. And then 1/3 times 24 is the same thing as 24m divided by 3. So 8m. And 12 divided by 3. I feel like I said this, but I'm not sure if I did this, that you could move things at the same time. So I'm going to do that. But if you need to see it separately, like one thing at a time, just let me know. So I'm going to pick something to move, and then move the other at the same time. A lot of the times when I move things, I don't keep things positive, so like move 8 by subtracting, so that I get a positive number. But if you wanted to move the 30 over, and you end up with a negative, that would be okay too. So I'm going to do that, and because I move my variables to the right, I need to move my constants to the left. I'm going to do this at the same time. The 30s cancel. This leaves me with negative 22. This also leaves me with negative 22, but m and these cancel. And then I could divide both sides by negative 22. Any questions on how I solved that? Does anyone want to see that second way when you get rid of the fraction first? And then always make sure you're double checking to see, does this work? Is this the actual solution? I have checked this. And you feel free to check it. Remember, you can also put this into Desmos, just as it is, and it will give you some line where x equals. You would need to change your variables to x, not m. Desmos doesn't like other variables. But it would show you that m does equal 1 or x equals 1. Right. For number 7, we have two fractions equal to one another. How did we go about solving that? There's something we need to do before we can actually solve it. Cross multiply. We're going to multiply 3 to everything down here and 8 to everything down here. Anytime you see two fractions, you should be setting them, well, I'm sorry, if they're already equal to one another, you should be cross multiplying. The order in which you write this does not matter. If you end up with this on the left side, that's fine. It should work out the same. From there, distribute 3v minus 9 equals 8v minus. If something you want to move, I'm going to do these again at the same time. I'm going to move 3v by subtracting to the right. As I move my variables to the right, I need to move my constants to the left. I'm going to add 32 to the left. The 3v's cancel. This is 20. Myself over here.
Sorry, it's 23, 22.
That's alright. It's Monday morning. My brain's not working. Sometimes the answers you get to these are fractions or decimals. That does not mean you got it wrong. Especially when you get answers that are decimals or fractions, I would double check this. Does this work? I'm going to put this one in the decimals. The fraction one, it doesn't matter. Usually it does, but that does work. That is the answer we got. Questions on that one? I'm going to give you about 5 minutes to work through any problems on this, and then we'll come back, and then we'll go over a couple more examples on the last notes, and then we'll be done for today. All right, let me get your attention on floor. And we're going to go through one of each type of these special cases. It kind of already says what they are, and this may be familiar to you. But just to explain it when you see it, you will get problems that look like all the problems we've done before. So the process to solving them is the same. Here I have something I can distribute. I'm going to go ahead and do that. I have like terms on the same side that I can combine. And remember, on the same side, you're just doing whatever operation it says. So 15 minus 10. Looking at just this, before we continue to solve it, what is similar and what is different about both sides of this equation? They both have that 5x. That's what's similar, what's different.
The assumptions.
So both, really. The constants are different. after we continue solving this, you'll see why that piece of information is important. So continue solving this. I'm gonna do this all at the same time and then also show you if you did it separately, what answer you might get. So if I go ahead and let's say I want to move this over here and then move the 5 over to the right, well, these are going to cancel and these are going to cancel, leaving just 0 equals negative 12. And that would be a no solution. That can't work. 0 doesn't equal negative 12 ever. So this would be a no solution. When you have a no solution, when you go to check it, there's no answer that will ever work. If you want to write this down, I'll look it up. No answer that would ever work for it. You can put in 100, you can put in 5 million, negative, decimal, it doesn't matter. Whatever number you put in this will never work. You will never get a solution. No solution. And some of you are trying to write, and I'm going to do it. If you were doing this separately, so usually one of the answers you'll get is like 0 equals some number. Or if you were doing this separately, let's say I just compare my variables instead of doing them at the same time, you might get something like the constants equal one another. And from there, you don't need to continue to do them because there's nothing for you to really solve. And I can say at this point that these two numbers aren't equal to one another, and that's still no solution. You can have one solution, you can have none. Let's try the second example. Same thing, it looks like a regular equation. So I can go ahead and distribute. Oh, sorry. I'm going to finish writing this really fast and then go back to this one. The reason why I asked what's similar and what's different for this one, if you are solving a problem and you get to some point where the constants, the coefficients are the same, but the constants are different, that should already tell you, like light bulbs should be going off, bells should be going off. This is going to be no solution anytime you see that. Now, if this was negative 5 and positive 5, then it's going to work out to be one solution because the coefficients are not the exact same. But if they're exactly the same and these are different, it'll be no solution every single time. Solving number 2. Oh, that was not 16. 6. There we go. And then, what do you notice about this one? They're exactly the same on both sides. That will help us determine what this solution is here in a second. So again, solve this as a normal problem. Subtract 16 on both sides, add 10 to both sides. And what happens in this case is that this cancels, this cancels. You're going to put some 0 equals 0. It is a true statement, but I don't have any variables left to say like x equals 0 or something like that. So when your variables disappear and you end up with a true statement, this is infinitely many solutions. Let's go that way. I'm sure it's on the paper. So in this case, anytime you have infinitely many solutions, that means every number could work. You can put in whatever positive, negative, decimal fraction number to check this, and it will always work every single time. The amount of solutions it has are infinite. So you could get one or two answers. You'll either get a 0 equals 0 if you do both of those things. I'm going to rewrite this real fast. If I just got rid of the variables, I'm left with whatever the constants are. That still tells me I don't have variables, but it's a true statement. I would still end up with infinitely many solutions. So if you start solving a problem and you see that they're exactly the same on both sides, the coefficients are the same, the constants are the same, you get infinitely many solutions every time. Questions on that? We have about 11 minutes left. With those 11 minutes, if you wanted to continue working through these examples, or the last page of additional practice, you're more than welcome to. If you wanted to get a head start on the Delta math that is due tomorrow on this, you could do that. Or if there were problems from the other page,